Okay, so we're going to start off with Jensen's inequality. This inequality states that the expected value of a function of the asset, okay, is greater than or equal to the function of the expected value of the asset. This is only true for functions which are convex, that is the ones which increase, okay, this way, that is where the first derivative that is there is always positive, okay, or the second derivative that is there is always positive, okay. So what this thing says is that the expected value of a payoff determined by the stock price is greater than or equal to the payoff of the expected value of the stock price, okay. So why this inequality is important is because generally when you're looking at stock prices, right, when you're looking at stock prices, okay, you basically try to figure out, generally people talk about, okay, what would be the expected stock price tomorrow or the expected stock price in the future. But just because you're having the expected stock price, if you're going to evaluate the payoff function, okay, using the expected stock price, okay, just substituting the expected stock price in the payoff function, that will not give you the expected value of the stock price, okay. There's a difference over here, okay. We will what the difference is coming about, I'll be talking about a little bit below. But just as far as deriving this inequality, let us consider this function over here is convex. This is the definition of convex function, okay. At 2 points x1 x2, define a point in the middle. This thing is simply, it could be written as this thing, alpha x1 plus alpha 2 x2, where alpha 1 plus alpha 2 is equal to 1. The thing would give you a point somewhere in the middle. Next, consider the values gx1 and gx2 over here, okay. At this particular point x, because of the as far as this line goes, it's a line. So if this thing was alpha 1 x1 plus alpha 2 x2, the corresponding point on this line that is there is just going to be alpha 1 gx1, alpha 2 gx2, okay. Now if you're looking at this line, you can look at, because see the convex function, the value of the function over here is g on that particular curve. It is g of alpha 1 x1 plus alpha 2 x2. So we can just see, look at it in the picture, that this relationship holds true, okay. Now by induction, what you could do is you could prove the following: g of alpha 1 x1 summation to alpha 1 xn, okay, that is equal to alpha 1 plus alpha 2 plus dash dash dash. As long as this thing is equal to 1, this thing is smaller than the sum of these gx's multiplied with the alphas, because the alphas are like probabilities, okay. What this expression on the right basically says is that we could understand this expression on the right as the expectation value of gx, because expectation value, if you're going to calculate, what you're going to do, you're going to take g, evaluate the value of x is equal to x1 multiplied with a particular probability, and then sum it off with all the values of g. That thing will be the expectation value of g x, okay, expectation value of gx, okay. Similarly, this function, this thing that is there, so that is why you have this thing, the expected value of gx. On the left hand side, what you're having is probabilities multiplying x. That thing is just the expected value of x, because the expected value of x is just x multiplied by the probability of realizing a particular value of x, summed over all possible values of x. That is what we could write this as. So then this is the expression that we get, that the expectation, the payoff function of an expected value of a particular asset is smaller than the actual is smaller than the expected value of the payoff function, okay. Now as I said, the difference that is there, we could try to understand the difference by looking at fluctuation around the average value of s. So if I'm having the average value of s, if I call it s bar, let me consider fluctuation along this s, which is equal to epsilon, such that it could either be positive or negative. So the expected value that is there of this is equal to 0. Then E, expected value of the payoff function, okay, is equal to expected value of f times, which is s bar plus epsilon. You Fourier transform, you Taylor expand. This is just f evaluated s bar plus epsilon times f prime s bar plus 1 half epsilon squared times f double prime s bar plus dot dot dot. Okay. Now expected values that are there of a thing which is already a particular value that you're taking. Okay. That thing is just going to be the f times s prime. Okay. Over here you will have to take the expected value of epsilon, which is equal to 0. Over here you will have to take the expected value of epsilon squared. Okay. So this is what we get: f of s bar plus 1 half second derivative evaluated s bar plus expectation value of e squared epsilon squared. So what we see is that, okay, the expected value of the payoff is greater than the payoff using calculated using the expected stock price, and the difference that is there is dependent upon two things. One is how strongly this thing is the function is convex, and second thing that will depend is the random component. How much is the randomness in the stock price? Okay, so the randomness in the stock price would basically tell you like how badly your evaluation of the payoff function using the expected stock price is going to mismatch with the expected value of the stock price, expected value of the payoff. Okay, this randomness that is there, more the randomness, more will be the difference between the expected value and the expected value of the payoff, and the payoff calculated is the expected stock price. Okay, now let's go below. What we talk about is the thing is, the returns that are there, as we have been talking before in the lectures, are basically the difference between the stock price from one day to the other divided by the stock price. Generally in the financial tables, generally financial data sets are the stock price every day, so you can evaluate the returns from one day to the other. Why the returns are important? Because for 1,000, say like a stock which is valued 1,000 rupees, it changes by like 1 rupee. That is not so much of a change compared to a stock which is valued 100 rupees, which changes by 1 rupee. So always the normalized change with respect to the original stock price is important. That thing is of more value, okay, because that thing will tell you how well the stock is doing. Okay, so then what we have is so in essence, in case, for example, if I go over here, I'm having the stock price for a particular stock inside the book. It's stochastic, it is increasing in value. Okay, if I look at the returns are always like this. Some of the returns at a particular day will be up, some of them will be below, and this way you'll be having a bunch of returns over here. Okay, you take these returns and then you basically look at how many number of returns that you're having. What you will have is that you will have a very large number of returns around a particular point, which is called the mean value of the returns, and then you will have that various other returns that are there are away from the mean in each direction. The number of returns that is there will be more or less be similar. Okay, so if you're basically looking at this, instead of plotting the numbers over here, they have plotted the probability of the return, where they look at number of the returns divided by the total number of returns which are there, all the returns that they have in their hand. Okay, then what they see is that as the number of returns, basic number of days that you're using, the number of returns that you have in your hand is made very, very large, then you see that these returns that are there, they will be falling under a curve, under a bell-shaped curve. This thing is called a Gaussian curve, or it's the normal distribution. And you can just see that over here, there's the mean value of the return around the mean value at the same value of the same difference from the mean. The values are more or less the same. Okay, and the way you would plot it is by looking at this kind of a plot: r minus r mean square divided by 2 times the variance. Okay, generally this is how these curves are. So this is the distribution of the returns. It's called the normal distribution, and this is generally how, like, it is approximated. The stock price are approximated, and this is how generally things are modeled. Okay, so as far as the time scale goes, the problem, instead of normally what we are saying is that, okay, we're looking at day-to-day variations. Let us, for example, instead say that how the stock price that is there changes in a time delta t. Okay, then this r mean that is there, is going to be going as linear function of delta t. The reason for that is that on an average, this is what we'll be expecting. Rmin is going to go as uh, mu times delta t, because more the time that is there, okay, more you would have expected the function, the change, more you would have expected, sorry, more you would have expected the change in the stock price. Okay, so longer the sampling time, more would the asset have moved. Okay, so in case we had ignored complete randomness, okay, that is over here we had ignored all this randomness that is happening. Okay, on what we would have seen is that Si minus Si divided by this is equal to mu times delta t. What we have is the following: Si plus 1 is Si times 1 plus mu delta t. If we had considered m intervals, time intervals, what we have is, in the limit delta t is very very small, this thing is just S0 times exponential of mu m delta t. Okay, so what we have is, in the absence of randomness, the growth that we there see is an exponential growth. Exponential growth in the returns. This thing is just almost similar to what we had when you took the money and put it inside a bank. Okay. Now, the thing is, in the presence of randomness, what you have instead is, you will have this other extra factor. Okay, sigma times the factor that is going to be this factor that is there is delta 1/2. This thing we had seen in the binomial case, binomial tree. There the stock would only have two values, up and down, and the up and down values was delta t. Okay, the range that is there, u minus v, that is there, of stock values was going as delta times sigma t. Okay, similarly over here, this is also telling you that the range that is there is proportional to sigma times delta t raised to 1/2. Okay, and phi that is there is picked up from the Gaussian distribution. Okay, so in case there were just two values, we could have just approximated it by u1 plus sigma delta t, 1 minus sigma delta t. Okay, when it's a continuous set of values, what you have is that the value at each particular time is basically picked up with the phi from this probability distribution, such that this thing has an equal probability of going up and down, times a particular factor, sigma times delta t, which is the remnant of the binomial tree. Okay, now the thing is, if you're looking at this r hat, which is taking the values of the returns, average value of the returns over m days or m time intervals, the main thing is, when you're taking the average, what you will be doing is taking the r hat here, you're going to take an average here. One factor is mu dt, which is mu dt times m. When you're going to be summing over this over many returns, the phi that is there is going to be equal probable plus with a plus and a minus value, so average value of this thing is going to be equal to 0. So when you evaluate this thing is just mu m dt divided by m equal to mu del t. Okay, so this mu that is there is called the drift rate, expected return, growth rate. Okay, and the unit of time as it is advertised, the drift rate, normally when it will be told to you in a financial lingo, normally the way it is advertised is this unit of time that is advertised is the year. So normally it will be called, like, say, the annualized growth rate, annualized expected return, or the annualized drift rate on a particular stock. You could also evaluate this phi, the way the sigma, that's what it's called, the sigma, right? Yeah, the sigma that is there, the way you would be evaluating that, you could evaluate that is by considering m time intervals and looking at this quantity. Okay, this thing is called a volatility, and the deal with the volatility is that it becomes important at shorter time scales. Because of the shorter time scales, delta t dominates dt, delta t raised to 1/2 dominates dt. So at the shorter time scale, this portion is important, so volatility is important. At longer time scales, mu dt will dominate, because dt dominates over delta t raised to 1/2. This thing is delta t, everything is delta t over here, delta t raised to 1/2. So at the long time scales, drift dominates, lower time scales, volatility dominates. If you are looking at This particular line that is there is a line with the slope mu, so this thing is mu delta t. This particular line that is there is mu plus sigma squared. Okay, that is the value slope mu plus sigma squared. This is a small slope mu minus sigma squared. Okay, and then normally this the stock price for most part will be between these two lines, one standard deviation from the mean. Okay. Now, how would you generally estimate volatility? As I told you guys, you would be doing it this way. Okay, in the limit where delta is small, you could ignore r hat. Okay, because as I told you guys that in the limit delta is small, the volatility dominates. Okay, so because volatility dominates, that means the ri, okay, the variation that is there is much more higher compared to the mean value. Okay, so then what we have is this thing is, if you're writing at ri, right, you could basically write this thing is just going to be the summation over ri squared. Because it's summation over ri squared, we look at ri, that thing is dsi divided by si. That is just could be written down as d log of s, and this d log of s is basically just the difference between two values of log of s at neighboring time points. So that is just log of si plus 1 minus log of si. That is what I've just substituted here. Okay, this thing is an estimate of the volatility. Here there are a few points to note. Volatility will change with time, because depending upon the market conditions, that is going to tell you how much is the market stock price going to fluctuate. Okay, so even though when we are evaluating the volatility at a particular time, we'll be using 10, 20 or 30 past return, etc. This past history that is there might not be very accurate in talking about the future volatility, okay, of the stock. Okay, just note this particular part. Now in the limit, what we had done was, this thing was a discrete value of how the stocks returns would basically be changing, and in a particular time step, how would we be expecting stock returns to change. Okay, so in case we have a look, this thing was discrete time step. If you go to continuous steps, you get a Wiener process. In the continuous steps, what you do is the difference of the stock prices between neighboring time intervals, call it as ds. Okay, delta t, I'm writing this thing as dt over here, but just remember that this thing is a discrete time step. Okay, so delta t and dt was just the same in both these cases. The delta t basically becomes dt, which is 0. Okay, so the main thing is, as far as the drift term goes, you can basically just replace the delta t with dt. Okay, however, the delta raised to 1/2 term has to be considered with special care. The reason being that in the limit delta t goes to 0, we will have that this term is going to dominate this term. I've just told you that before. Small, when this thing is very, very small, this is dominating this term. So does it imply the drift is to be ignored? Actually not, because the other portion is that on an average, phi goes up and down with the same probability. So on an average, the mean value here is equal to 0. So then we are getting another constraint over here, that this thing will dominate at smaller values, but this thing mean is equal to 0, so this thing is important. So what is the right message as far as this term goes? So that is something that we will see right now. Okay, in order to see that and to simplify notation, just replace sigma delta t, this phi delta t raised to 1/2 with dx. So what we have is expectation value of dx, because this thing can go up and down with equal probability, is equal to 0, and the dx squared that is there would be going as some dt. Okay, because the expectation value of phi, if it is basically chosen from a Gaussian distribution, is equal to 1. Okay, that is, if it was chosen from a distribution that was given here, it is chosen from distribution valued here, write this as multiply by phi and integrate over all values of phi from -phi to phi. It's going to give you a value equal to 1. Not phi, sorry, phi squared I mean. So this thing is phi squared. Okay, so this expectation value is equal to dt. Okay, so the idea is that you could build a continuous time process using a Wiener process, And instead of, as I said, as far as a discrete process code, you had a discrete value of time, and then you had to choose phi from a normal distribution or a Gaussian distribution. In a continuous time, you just go towards mu dt plus sigma times a variable dx, okay, which is, and the dx has this property: exponential value is 0, expectation value of squared is equal to dt, okay. Now in order to build this up really, to make more sense out of this, to give you an intuition about the behavior of this dx, let us consider a separate problem. Consider a coin toss problem, where if you get a heads, you win a rupee, you get a tails, you lose a rupee. Then expectation value of the winnings, if I'm going to call the amount you win at each toss as Ri, that is amount won on the I tossed, then it's obvious expectation values of this is going to be equal to expectation value of Ri is going to be equal to 0, because you could either win a rupee or lose a rupee. Expectation value of Ri squared is equal to 1, because Ri squared is equal to 1 in value. 1 or minus 1 squared is equal to 1. And expectation value at two different time steps, two different coin tosses multiplied with each other is equal to 0, because this thing has an equal probability of being value equal to plus 1 or minus 1. That being said, let me define an SI, a sum SI, Sj, which is sum total of all the winnings that you have had. Okay. What we have is that Sj is equal to Sj minus 1 plus Rj. Okay. If that is the case, then we can define, there are certain properties of this process, of this particular interval. Okay. The thing is, this thing has a Markov property. That is the expectation value that you have of winning a particular value Sj, given that you have won Sj minus 1. Okay, it's just going to be, when you're going to be evaluating that, it is you have been given Sj minus 1, okay, plus the expectation value of Rj. Expectation value of Rj is equal to plus or minus 1. Expectation value of Rj was equal to 0, so this is just Sj minus 1. So the expected value of Si only depends upon the value, expected value of this winning tomorrow is only dependent on the value that you have today. This particular property is called a Markov property. Okay. Similarly, there is something called a Martingale property. This property basically states that the expected value, if I'm going to evaluate the expected value of any other particular time interval, any possible other times, given the value of the asset's value today, okay, that is just going to be the asset value today plus the expected value of all the other winnings, or the winnings on every other day, sum of all the winnings on every day in the future. That is equal to 0, so this is equal to Sj. So the expected value in the future is dependent on the value today. Okay, so as far as coin toss goes, this is what we are getting. Okay. Next, as far as this variation goes, as far as if we evaluate Sj minus 1 squared, we have it as Rj squared is equal to 1. So for I coin tosses, this sum that is there is just going to go as I. This thing implies a quadratic variation. That's the definition of a quadratic variation. Till now we have been talking about tosses. Let us include the time interval for this experiment. Let us say that n tosses had happened in a total time t, such that at each tossed, instead of making 1 or plus or minus 1 rupee, you make plus or minus t divided by n rupees. Okay. Then summation, this particular summation that is there, that was I, would instead go as n times you're making t by n at any particular toss equal to t rupees. Okay. Similarly, when we are evaluating other quantities, say like we are evaluating expected value of St, that thing is just defined, the expected value that you made at the time t is just an summation or all the winnings that you did in the n tosses, that is equal to 0, and the expected value of the winnings that you have squared is just expected value of it's just going to be Ri squared, expectation value of Ri squared, plus expectation value of Rj, and I is not equal to j. This is 0, and this thing is just the t by n divided by, this is just this factor, t by n times n is equal to t. Okay, so the reason we brought this up is because this thing is going to lead us to this example of Brownian motion. Right now, in order to first of all note that this particular model that I have used coin tosses, but this thing is called a random walk model, because what in case instead if we replaced the winnings at a particular time step as a random walker who could have moved to the left or to the right, okay, then s that is there determines the total distance he has moved. Okay, so this thing becomes like a random walker model. That is, if the number of tosses that is there is the total number of steps, Ri basically determines whether he has moved left or right, and s is basically the total distance that has traveled. Okay, so this thing is like the random walk model, and everything basically goes through, the definitions that are there, everything basically follows through whatever was there for the coin toss. Okay, this thing is, in the continuous limit, what happens is that this stuff that is there, the random walker, is basically the discrete random walk. In the continuum limit, it basically is called a Brownian motion. Okay, st that is there, let us call it xt from now on. This is just the xt that we had defined previously over here. Okay, so the thing is, this is where the way the stock price would basically, the random component of the stock price is, it follows a Brownian motion. Okay, and the properties of this x, the stochastic component that is there, are, it is finite. Okay, that is the expectation value of st squared is basically finite. It is just dependent upon t, as we have seen above. The Markovian distribution that is there in the continuous limit, the Markov property reads out like this, that the conditional distribution, okay, of x in the future depends upon the value x took today. Okay, Markov property becomes a property of the conditional distribution, okay, conditional probability distribution of the variable x in the future, and it is only dependent upon the probability today, not upon in case I have information till today. Okay, it is not dependent upon anything that happened before today. Okay, so this is what the Markovian property is. The Martingale property, on the other hand, says that the expectation value in the future of x is equal to the value that I have up till the latest value that I have. Let us say I have the latest value of x till today, then the expectation value any time in the future is just the value that I have today. Martingale property talks about the expectation value any time in the future given the latest value that you have, and if the latest value that you have today, then it's the latest value today. Markovian property tells you the probability distribution any time in the future. Okay, next what we have is the quadratic variation, that is the summation of all these x, the summation that you have of this term x, how it varies from one time interval to the other, squared of that over n time intervals is basically equal to the total time interval. Also, normality, x, the difference between the x at two consecutive time intervals, okay, that follows a normal distribution with a mean 0 and a variance tj minus 1. That is, it is this way. This is the probability distribution from which the value of this difference is getting picked up. This is the definition of a Brownian walker. Okay, using this particular definition, so x is basically a stochastic variable, it's a Brownian walker. Okay, it is getting the difference between the x's are getting picked up from a normal distribution. It is Markovian, it's Martingale. Okay, now how do you work around with it? It's a different kind of a variable from a normal variable. This is a stochastic variable. So how do we can do calculus with that? If we are doing integral calculus, we should be able to define an integral. The way we define the integral is any particular ft function at a particular time times d of xt will be equal to the limit n going to infinity. You consider n, you basically split up your particular time interval into n intervals, okay, such that n is going to infinity, evaluate the f at the time interval j and construct this difference between x evaluated at the time interval j and x evaluated at time interval j minus 1. That thing is the realization of this integral. Okay, this thing is just, the main thing to note is that ft that is there has no information about this. Okay, these are separate quantities. Okay, this is not w, this has to be x. Instead of writing the integral all the time, we just write it as this particular thing in the shorthand form. dw is f times dx. Okay, this thing has a property that the expectation value, okay, is equal to summation over ti minus ti minus 1 is basically the entire time interval. Okay, the reason being that x that is there, this thing that is there, the squared that is there, okay, if x is chosen, this difference that is just chosen from this distribution, the fact that the variance, this thing should basically equal to the variance that is there. Okay, the expected value of the square should basically equal to the variance. So this is all that this thing is telling you. Okay, expect each and every value of I is getting chosen from this distribution. The variance that is there is tj minus 1, or is ti minus 1 here, and then you're summing over all possible values of n. So that is why you get this expression. So next thing that we have to note is that thing leads to this expression. Okay, to see why it is going to be related to this expression, note that in the limit of very large n, what we have over here, this particular summation that is there is basically just, you're basically realizing this particular quantity. Okay, this particular realizations over n time intervals, right? And you're summing them. What we are saying is, we are looking at this quantity, the difference between x at one particular time with the neighboring time squared, that you evaluate it at one interval at one particular time, okay, and one particular time in the interval I. Okay, and then you basically evaluated all particular time intervals that are there in the process. So these are various realizations of the same process. Once you're having various realizations of the same process and you're summing them, that is equivalent to evaluating an expectation value. So this summation is equivalent to an expectation value of this particular term. Okay, because of that, what we have is that this term that is there, summing over all possible values of n, is equivalent to dx squared integrated over 0 to t, and that is equal to the expectation value of this thing, which we have evaluated to be equal to the time interval. So it is equal to the time interval. Okay, now next thing that we come to is the concept of functions of stochastic variables in the Pareto lemma. Naively, we would have expected that the function x equal to x squared would imply df is equal to 2x dx. But because dx, as I've said, is the x that is there is a stochastic variable, things would come out to be different, and we'll see how it's coming out to be different. What we do is we get another time scale. dt anyway is very small, okay, which goes to 0, but get in another time scale, which is dt divided by n. N can be very large. Okay, so this thing is an even shorter time. But let us get that into the picture. When we do that, let us evaluate the following: f of x t plus h minus f of xt. You can Taylor expand. There is one term which is just the difference between the x's times df by dx. This thing we evaluated at x is equal to t. Okay, this thing is xt plus 1/2 the difference squared times df by dx squared, where x is evaluated at t. Now we have that thing. What we can do is we can make a summation over j. We can basically do a summation. This thing, what this h basically implies is I'm taking the time interval dt and I'm splitting it into n time intervals. What I can do is evaluate this particular difference, okay, at any of these intervals. Okay, So this particular difference that is there is evaluated at any of these intervals. Let us call this interval j. Then you sum over all of these intervals. Summing over j is equal to 1 to n. You can do the Taylor expansion that you did over here. Similarly over here, there is a difference between the x's, df by dx, because x that is there, t that is there is like many orders of magnitude larger than h. Okay, you could just evaluate df by dx at h at a t. Okay, and then again you're having 1/2 this thing squared, the difference in the x's squared, times del squared f by dx squared evaluated at xt. Okay, now the thing is, the thing is, when I'm basically looking at this summation, right? This summation is basically just going to be equal to the value of x at t finally, and my subtracted from the value of x, subtracted from the value of the function f evaluated x at t plus delta t, which is equal to nh. Okay, similarly when we are looking at this summation, we are just going to be getting the difference in the x's here multiplied by df by dx, and then when we are having this particular term added up with the j is equal to 1 to n. Okay, now I use the statement that I had made above, that the sum of these squares, okay, is like taking an expected value of this expected value evaluation of this difference, that is this over here. Sum of these squared is equal to the expected values of this squared, which is equal to the time interval under consideration. Okay, so then I look over here, what I have is this thing should basically be equal to dt, and this is the Pareto lemma. Okay, where the change in df is dx times this derivative plus 1/2 this thing times dt. Now here then it gets you an interesting point. If f is equal to x squared, just plug it in over here. What I get is 2x times dx, looking at this expression. But now I'm getting something else. Second derivative with respect to x is 2. That cancels 1 by 2. This is 1 times a dt. So you see, when you're looking at stochastic variables, we have to consider this extra factor that is coming in. Okay. Now one could have just been lazy enough, and one could have said that f x plus dx minus dfx is just by Taylor expansion dx times second derivative times dx squared, and then lazily one could have substituted this dx squared as dt, and it turns out this is the way to go forward. Okay, that is what you do is you just substitute the expectation value of the average variable squared. Okay, whenever you are getting an average variable squared in this particular differentials, okay, in the particular differential, instead of doing this whole calculation above, what you could do is you could just take this dx squared and you could substitute it with this average value, expected value, and all the calculations goes through in the right method. Okay, for example, we could see this example in case the asset price is having this formula, the dt and dx both are functions of s. Then an option that is there, it is the functional dv, so we could just expand it this way because of this formula. Replace f by v, look at this formula, look at this formula. Okay, look at the first look at the first formula, forget that, look at the first formula. Okay, don't look at this formula over here right now, look at the first formula, substitute f with v, x by s, we get this formula. Okay, this thing was just a Taylor expansion. Now what we do is we substitute the value of ds squared. What I say is take the average value. When I take the average values of the squared, first thing I will get is dt squared. I ignore that because I'm only considering terms of the order of dt. This thing that is there, I will have a cross term. Average value is equal to 0 because average value of x squared, or the expected value, is equal to 0. Then expected value of x squared dx squared is dt multiplied by that by the b squared. So this is what we get, and it will work out fine even though we had just gone through this whole just replacing this thing by the average value. Okay, because that is what is the final conclusion that is coming out in most cases when you do this easier methodology of using Iato. Okay, instead of doing the Iato calculation that we had done previously, if we just replace the average value of the of dx squared anywhere we find it, average value of d of a fluctuating quantity squared. Okay, you can just replace that with this average value, and then everything turns out to be right. Now let's consider a process, a log normal walk, where ts changes by the drift. That is what we had initially in the problem. What we said is how stock prices change. That is generally how they are modeled. Mu s ds plus sigma s dx. If I replace, if I consider f is equal to log of s, okay, then the thing is I just use this formula. Okay, I just use this formula. One second. Okay, because of the b that is there over here in this particular case, this is how we have started with the stock price, right? If this as is basically just mu s, bs is just equal to sigma s. Okay, that means df that is there is just df divided by ds plus 1 over 2, plus that is what we have. Call the f that is there, whatever we had v over here, call that as f. If we call that as f, then what we get, this thing is just df is equal to df s divided times ds plus 1/2 df squared divided by ds squared, okay, times whatever the b that was there. It is sigma times s over here, so it's sigma squared s squared times 1/2 times dt. Okay, once we have that, we make a substitution of what substitute what the value of ds is over here, which is just this particular term. So that is the term above. Substitute what derivative of log of s is, that is just 1 over s. Similarly, substitute what second derivative of f is, second derivative of log of s, which is just minus 1 over s squared. That will multiply the s squared here and give you a factor of minus 1. There's a 1/2 sigma squared dt. Okay, with that in mind, then what we have is this term that is there is just a term which is multiplied by dt, mu minus 1/2 sigma squared plus sigma times dx. This thing is a differential equation. When we solve it this way, that is just this thing times t plus initial and final values of x. F is log of s, so s is equal to s naught times the exponential of this term.